Hello. We'll continue our discussion on Savitri Veda, Max Fogg New Age Mother. Today we will be discussing about thinking, reasoning about probabilities. So we will see that she issues, some challenges, and how to deal with it. We will take an example from it. See, actually, there is a book called Calculated Risk. So the author is a cognitive psychologist, and he has tried to discuss the issues in interpretation of medical tests. And he explores how people miscalculate risk and uncertainty. But rather than scold, bemoan human frailty, he tells us how to do better, how to avoid cloud thinking by recasting conditional probability problems in terms of natural frequencies. Here he is giving he is identifying a problem in human reasoning, and he is trying to give a way to solve it. In one study, the researcher and his colleagues asked doctors in Germany and United States to estimate the probability about whether a woman has a breast cancer. Whether a woman who has a positive mammogram, the test has been taken, test is positive. Actually, now the question is whether she actually has a breast cancer or not. Even though she is in a low risk group, 40 to 45 years old, with no symptoms or family history of breast cancer. So she is a low risk group. But the result is positive. So how to make judgment? To make the question specific, the doctors were told to assume the following statistics, couched in terms of percentage and probabilities, about the prevalence of breast cancer women in the cohort, and about the mammogram's sensitivity and rate of false positive. False positive means the person doesn't have cancer, but the test result says positive, that she has got a cancer. The probability that one of these women has breast cancer is 0.8%. If the woman has breast cancer, the probability is 90%, then she will have a positive mammogram. This is a simple case. Cancer is there and the result is also say so. If a woman does not have breast cancer, the probability is 7% that she will still have a positive mammogram. This is false positive. That is, he doesn't have cancer, but you get a result that she has got a cancer. Now imagine a woman who has a positive mammogram. What is the probability that she actually has breast cancer? So now you have to, this is a challenge. So the researcher describes the reaction of the first doctor he tested, a department chief at University Teaching Hospital with more than 30 years of professional experience. He was visibly nervous while trying to figure out what he should tell the woman. After mulling the numbers over, he finally estimated the woman's probability of having breast cancer, given that she has a positive mammogram, to be 90%. So he is taking the normal efficiency of the test equal to the probability of the woman having cancer. Nervously he added, "Oh, what a nonsense, I can't do this. You should test my daughter. She is studying medicine." He knew that his estimate was wrong, but he did not know how to reason better. Despite the fact that he spent 10 minutes wiggling in his mind for an answer, he could not figure out how to draw a sound inference from the probabilities. Here the challenges with the probability statistics details. The researcher asked 24 other German doctors the same question. They estimated from 1% to 90%. So they had different values. 8 of them thought the chances were 10% or less. 8 others said 90%. And the remaining 8 guessed somewhere between 50 to 80%. Imagine how upsetting it would be as a patient to hear such diverse opinion. As for the American doctor, 95 out of 100 estimated a woman's probability of having a breast cancer to be somewhere about 75%. Now you see the point. The right answer is 9%. Now what he says, how can it be so low? The researcher's point is that analysis becomes somewhat transparent if we translate the original information percentage and probabilities into natural frequencies. See, here the same information given in a different form. 8 out of every 1,000 women have breast cancer. This is sensible. 0.8 is written this way. Of these 8 women with breast cancer, 7 will have a positive mammogram. This is the 90% efficiency of the test. This is told this way. if 8 women with breast cancer, 7 will have a positive mammogram. Now you see the actual population which doesn't have breast cancer is 9992. Of the remaining 9992 women who do not have a breast cancer, there also will get a positive result, positive test result. Some 70 will still have a positive mammogram. See, now you see the 70 people are the false positive. So imagine a sample of women who have positive mammogram in screening. How many of these women actually have breast cancer? See, now you see how many people have actually positive mammogram? 7 in the actual breast cancer group, 70 in the actual non-breast cancer group. So this is a total of, since total of 7 plus 70, 77 women. Out of 77 women, only 7 has the breast cancer. 77 women have got positive mammogram. But of these, only 7 of them truly have breast cancer. Okay, the probability of a woman having breast cancer given a positive mammogram is 7 out of 77, which is 1 in 11, which is 9%. So here what he has done, by giving the information in a more intelligible form, we can make proper research.